Hi, my name is Kate Sharabira, and this is my Physics 2212 lab report number 1. The purpose of this lab is to experimentally determine the charge of a piece of tape that's suspended in the air due to electric and gravitational forces. Then I'm going to create computational models of the procedure and compare results. A preview of the main result is that the charge for each piece of tape is these values. Some fundamental principles. First, we have gravitational force near Earth's surface, which is going to be mass times g. In this case, g is 9.8 meters per second squared. We're also going to use Newton's second law, which states that force equals mass times acceleration. And we're going to use this to conclude that if there is no acceleration, then the net force must be 0. We're also going to use Coulomb's law, which states that electric force is equal to k times q1 times q2 over r squared. For the experiment, some background is that the system is tape A and tape B, and the surrounding is like the hand, the table, and everything else. For the initial conditions, both tapes are neutral. For the procedure, first we have to create 2 negatively charged tapes, and we're going to do this by sticking a U-tape to a base tape and then ripping it apart. Do this twice, and then that becomes tape A and tape B. And then the second part, we raise tape A under tape B until tape B is suspended in the air, like figure 2 right here, and then record the distance between the 2 tapes. Some observations: the length of my pieces of tape were 0.2 meters, the mass was 2 times 10 to the negative 4 kilograms, and the distance between the 2 tapes was 0.02 meters. Calculations. First, we calculate gravitational force by using m times g, and in this case, the value is here. And then the magnitude of the electric force is going to be the same as the gravitational force because F net is 0, and that's because the tape is floating in midair and therefore has no acceleration. So yes, we just use the magnitude of gravitational force. And then for the measured electric charge, we use the equation for electric force and rearrange it to solve for Q. We do have to assume that the charge of tape A and tape B are the same for this to work. For my first computational model, I assumed that the tape was a point charge, and then I basically just entered in the mass and the distance, and this was the output. And then I used this output to enter into my second model, which models the tape as a line charge, and so the estimate goes here, the mass goes here, and then the rest of this code is just just estimating the tape as a line charge. And then here's the output. As you can see here, all the white lines are the individual charges, and then you add them up and get this big blue arrow, which is all of the electric force going up. So recapping, the magnitude of the charge on one piece of tape in my first model was around 9.33 times 10 to the negative 9 coulombs. For the second model, it was 6.765 times 10 to the negative 9 coulombs. For the second model, I had to take the electric force that was from the output and solve for Q using this equation. For the first model, it just directly gave me this as an output. So, and I also had to use some assumptions to make sure that my code ran. The first one was that both tape A and tape B had the same charge. I had to assume that there's no air resistance, and then that the tape is a point charge and a line charge, respectively. Results, we can see that the line charge model estimates that the Q is smaller than it does for the point charge estimate. We can compare the numbers here. They're in the same power of 10, but still a little bit different. So what accounts for these differences? The line charge and point charge are calculated differently. There's also some experimental error, like maybe incorrectly measuring the tape mass, and then also maybe my assumptions were incorrect. For the discussion, what happens if the signs were reversed for protons and electrons? This wouldn't really change my observations, since if the tapes were positively charged, they would still repel each other, and the magnitude of charge would be the same, and so the electric force would be the same. And then why do the point charge and line charge models have different computational values? So they calculate the electric field in different ways. The line charge model uses integrals to add up all the charges along a line, while the point charge only uses one value. The line charge is most likely closer to the truth because the tape is a line and it's not just a point. Thank you for watching.